Assalamualaikum and a very good day to Dr. Azwan. In this video presentation, we are going to present our heat transfer project on passive cooling. This group consisted of 4 members including me, NURUL FARESHA, Puteri ANDRIANA, MOHAMAD ADIB ALAUDDIN and NURSYAZA ADHA.
So Bismillahirrahmanirrahim. So first part for this presentation is introduction. So we go through for introduction. So first is operating condition for this case. So for this case, ambient temperature is 30 degrees Celsius and maximum allowable chip temperature is 85 degrees Celsius and cooling mode is natural convection. Alright, so second is material. So for this case, we are using the aluminium alloy 6061. So it's good for thermal conductivity and structural suitability. So third is a physical constraint. So base size for this case or for this chip is 60 mm multiple by 60 mm. So height is less than 50 mm. So 4 is passive cooling, so no moving part, which is higher reliability, lower cost, minimal maintenance and simpler construction compared to the active cooling system. So 5 is the objective for this case. So objective for this case is to assess a passive heat sink system thermal performance, to calculate thermal resistance, effective surface area and then field efficiency. And we use SolidWorks flow simulation to verify the theoretical investigation. And then last but not least is to carry out a study on design optimization. So we move to the specification for this case. Like we can see at the table, heat source Q, we have 10 watt and ambient temperature T ambient, which is 30 degrees Celsius, and maximum chip temperature is 85 degrees Celsius, and heat sink material is alloy 6061, which is K there around 170 W/MK. So maximum base size is 60 multiple by 60 mm. So maximum height is 50 mm, and mechanism for this case is natural convection. Right now we move to the methodology part. So for phase 1, base case calculation. So by reference to the table that I attached with the FBD diagram, so we can see here type of fin for this case is a rectangular fin. So base area is based on their base, which is 60 multiple by 60, and base thickness is 5 mm, and then number of fin for this case is 10. Thickness of fin we got 2 mm, and then corrected fin length LC, which is 30 mm. So convection coefficient H for this case is 8. Now we move to the calculation. First we need to calculate the fin efficiency. So to get the efficiency, we have the rectangular fin formula, which is fin efficiency is equal to tan H MLC over by MLC. So if we want to find the efficiency, we need to find M first. So formula for M is square root 2H over KT. So based on the table, we can get the value of M and sub into the formula, and then we got the value M is 6.86. So since we have a complete data, so we can calculate the fin efficiency. So by substitute all the value, so we got the value of fin efficiency is 0.9861. So second, we need to calculate the effective area, AEFF. So based on the formula, effective area is equal to A base, area of base, plus N multiple by area of fin and multiple by fin efficiency. So as we know, area of base is 60 multiple by 60, so we got the 0.0036 meter per square for area base, and area of fin we can use the formula area of fin is equal to 2WLC, which is, and we got the value area of fin is 0.0036 m square also. So since we have a complete data, so we can get the area of effective area, which is 0.0391 meter per square. Now we want to calculate the convection and conduction resistance. So third is we need to calculate the convection of resistance, which is R convection lah. So R convection, formula of R convection is 1 over H multiple by effective of area. So we substitute all the value that we get So we got the R conversion is equal to 3.1969. So 4 is a conduction resistance of the base, which is R conduction. So by using the formula R conduction is equal to T base over K multiplied by area of base. So we got the value of R conduction is 0.00817. So last but not least, for base calculation is we need to calculate the chip temperature. So the chip temperature formula is T infinity plus Q multiplied by R convection plus R conduction. So we substitute all the value, then we got the chip temperature is 62.05 degrees Celsius.
So my name is ANDRIANA binti HASNIZAM and my matrix number is AD230018. So let's move on to the simulation methodology part. For the second phase of this project, focus on utilizing model engineering tools to validate the accuracy of the theoretical calculation events Y. The primary objective is to develop a 3D model according to the base specification and conduct a computational fluid dynamics in simulation using SolidWorks flow simulation software. So we need to produce or conduct a 3D model based on the base specification that given in rubric group assignment. So the figure above shows a surface plot temperature of solid in degrees Celsius of the base case heat sink, which reach a converse solution at iteration 1 to 2 with 4 different views, which is the top view, side view, front view and isometric view. The peak temperature is 78.22 degrees Celsius, successfully meet the design constraint of remaining below 85 degrees Celsius like base specification given in rubric assignments. So the isometric view also displays the fluid geometry and air domain required to a natural convection. So the velocity curve plot visually demonstrates the principle of natural convection. Theoretically, as the heat sink conducts thermal energy from the chip, the surrounding stagnant air warm-ups becomes less than and rises due to the buoyancy. This creates the vertical flow trajectory seen in the streamline, reaching a maximum velocity of approximately 0.415 meter per second. The converged maximum solid temperature of 78.22 degrees Celsius remain consistent across these views. Confirming the design successfully dissipates the 10-watt heat of volume source that the instruction suggests plug into the ambient environment while staying below the 85 degrees Celsius temperature, which is the safety limit temperature of the chip. Thus, it is a gold plot graph that proves that the maximum chip temperature successfully stabilized at 78.22 degrees Celsius by iteration 1 to 2, providing a reliable and converged data point that confirms that heat sink operates safely below the 85 degrees Celsius safety limit temperature of chip. The red curve illustrates the thermal transition from the 30 degrees Celsius ambient starting point to the final steady state equilibrium, where the 10 watt of the heat generated to the perfectly balanced natural convection and conduction of cooling. So let's move on to the part of design optimization phase 3. This project transitions into complex problem solving by conducting a parametric study to optimize the heat sink performance. Our group has chosen to manipulate the number of fins and type of fin as the independent variable to analyze its impact on the maximum chip temperature and the total mass of the heat sink. Theoretically, increasing the number of fins expands the effective surface area for natural convection. So let's continue to the computational mesh used to ensure numerical accuracy during the phase 3 parametric study. A multi-level approach was applied, applying a localized level 4 refinement to the fin array to precisely capture height, thermal gradients and fluid flow behavior. This high-quality mesh ensures the simulation accurately accounts for natural convection boundary layers, providing mathematically converged and reliable data for the design optimizations.
My name is NURSYAZA and administration. My metric number is AD230060. So in this slide, I will show about the phase 3 of the design optimization, which is in this part. We have like 4 iterations that we're going through for the simulation. So for the first one is iteration 1 of the heatsink simulation. Firstly, the design parameters such as the fin type, dimensions, material and operating conditions were defined based on what I have shown in the table here, which is a heat load is applied of 35 watts and the ambient temperature is 25 degrees Celsius. Next, the heat sink model was simulated to analyze its thermal performance, where from the thermal simulation results, the maximum temperature obtained is 70.6 degrees Celsius, which occurs the base of the heat sinks where the source is located. Therefore, the temperature gradually decreases along the fins, which indicates that heat is being effectively transferred from the base to the surrounding air through the convection. Overall, this iteration shows that the heat sink is able to dissipate heat, but further optimization can be carried out to reduce the maximum temperature. Here also I have conduct the graph simulation based on the simulation parameters. Last but not least, iteration number 4. For in this iteration, we're focusing on the heat sink simulation again, but the type is different. Which is, in this iteration, the heatsink design was modified by increasing the number of fins and adjusting the base dimension and fin height, as shown in the parameter table that I have conducted here, where the simulation was conducted with a heat input of 15 watts and the ambient temperature of 25 degrees Celsius, which based on the thermal simulation results, the maximum temperature recorded is 53.5 degrees Celsius, which also occurs at the base of the heatsink near the heat source. The temperature distribution shows a more uniform and lower temperature along the fin, indicating the improve of heat dissipation compared to earlier iterations, which is iteration number 1. Overall, the iteration 4 demonstrates a significant improvement in thermal performance and shows that the optimized heatsink design is more effective in reducing the maximum operating temperature. Also here, I have conducted a graph simulation to show the maximum temperature the iterations conduct. That is all about phase 3 design optimization based on different type of iterations.
So let's move to the iteration 3, design optimization. We manipulate the fin type, which from the rectangular fin type we change to the cylindrical pin fins with 25 pins that we array 5 row and 5 column. So the others parameter we choose to remain constant, like base case specification, just change the fin type. So this is the graph tracks the maximum chip temperature of a simulation iteration for the pin fin design. The solution stabilized at approximately 81.04 degrees Celsius, demonstrating a steady state result that remains safely under the 85 degrees Celsius limit. The sharp initial rise reflects rapid heat pull up, followed by stabilization and natural convection balance to the 10 watt heat load from the volume source that we attach in the microchip. So let's move to the last iteration, which is the iteration 4. So we decide to manipulate the number of fins for this iteration 4. We manipulate the number of fins, we've changed to 12 number of fins for the fin type, which is rectangular fins. So other parameter we remain its constant, just change the number of fins only. So the isometric thermal plot view reveals how heat spreads across the 12 fin array. So the graph tracks the maximum chip temperature over simulation iterations. The solution stabilized at approximately 83.03 degrees Celsius, showing a steady state result under natural conditions. Although this design stays safely below the 85 degrees Celsius limit, within a safety limit for the microchip, the temperature rise compared to the base case suggests diminishing returns from adding more fins. So this not a really good suggest because the temperature is nearly to 85 degrees Celsius.
This section summarizes results from both manual calculations and SolidWorks flow simulation, including a comparison of analytical and simulation temperatures for the base case design, visual observations from temperature and flow plots, and outcomes from the parametric study conducted in phase 3. The initial heat sink design was evaluated through manual heat transfer calculations, yielding a predicted maximum chip temperature of 62.05 degrees Celsius, which is below the allowable limit of 85 degrees Celsius. Additionally, this design was assessed using SolidWorks flow simulation under natural convection with the resulting maximum chip temperature compared to the manual findings in Table 5.1. The analysis reveals a significant discrepancy between analytical predictions and simulation results for a base case heatsink with an estimated maximum chip temperature of 62.05 degrees Celsius compared to 78.22 degrees Celsius from SolidWorks flow simulation. This discrepancy underscores the limitations of simplified analytical methods, while the simulation accurately reflects three-dimensional heat conduction and realistic airflow under natural convection. Despite the variations, both temperatures are below the maximum allowable limit of 85 degrees Celsius, indicating that the design remains within safe operational parameters. The plots diagram illustrates air movement around a heatsink due to natural convection. The velocity cut plot shows how heated air rises vertically between the fins while cooler air replaces it from the surroundings, confirming natural convection as the main cooling mechanism. The airflow path suggests that fin spacing permits adequate air movement for effective passive heat removal. The temperature cut plot indicates that warmer air is located near the heat sink surfaces, while cooler air is found further away. This distribution demonstrates effective heat transfer from solid surfaces to surrounding air with a gradual temperature decay that reflects strong thermal interaction during steady-state operation. The flow trajectory plot illustrates continuous airflow paths around the heat sink due to natural convection, with air rising and forming thermal plumes. Fresh air circulates from the sides, confirming that the geometry allows stable airflow patterns for passive cooling applications. A parametric study was conducted to assess how changes in fin configuration and quantity influence the maximum chip temperature, involving multiple design iterations that were simulated and benchmarked against a base case. The study reveals that fin configuration significantly affects maximum chip temperature. The base case design shows a temperature of 78.22 degrees Celsius within acceptable limits. Among modified designs, the rectangular fillet fin achieves the lowest temperature of 53.50 degrees Celsius, while higher fin density or alternative shapes lead to higher temperatures, suggesting diminished cooling efficiency. The findings highlight the critical role of fin shape and spacing in improving airflow and heat dissipation.
The discussion part. First is a graphical comparison of parametric study. So first graph is a graph of maximum chip temperature against design iteration. So as you can see here, for design iteration 0, which is for base iteration, is we get the maximum temperature is 78.22. So design iteration 1 is 53.5 degrees Celsius, and then design iteration 2 we got 70.6, and design iteration 3 we got 81.04, and design iteration 4 we got 83.03. So we move to the graph of maximum chip temperature against a heat sink mass. So we use the same temperature that we got from different design iteration. So first we got 53.5 degrees Celsius. So we got the heat sink mass is around 78 until 79. So for 78.22, which is base punya iteration, we got around 1150 until 1117 for heat sink mass, and 70.6 we got around 130 gram heat sink mass, and for 81.04 degrees Celsius we got around 178 gram for heat sink mass, and then last but not least is 83.03 degrees Celsius. So we got around 183 gram heat sink mass. Second is a discussion of parametric study. So for this part, we need to calculate the percentage error so that we can know how much error that we got. So first thing first, by using the formula percentage error, simulation temperature minus calculate temperature over the calculate temperature multiplied by 100. So we sub all the value that we get. So the percentage error is 26.1%. So which is a not higher percentage error. It's a good. So for this case, parametric study outcomes demonstrate that fin geometry significantly affect thermal performance. So first is iteration 1. Iteration 1 achieved the best performance, reducing the maximum chip temperature to 53.5 degrees Celsius, 24.7 degrees Celsius drop from the base case, which is from the 78.22. So for iteration 2 show moderate improvement, which is from 70.6 degrees Celsius, indicating that fin spacing and count also play important roles. So iteration 3 and 4, performance worse than the base case, with the temperature rising to 81.04 degrees Celsius and 83.03 degrees Celsius, likely due to the restrict airflow or poor natural convection pathways.
This project assessed a passive heat sink's thermal performance for an electronic chip under natural convection. The analysis and SolidWorks flow simulation revealed that the original design maintains a maximum chip temperature below 85 degrees Celsius, though simulation results suggested slightly higher temperatures due to three-dimensional heat conduction and airflow dynamics. A parametric study showed that fin geometry and spacing significantly affect heat dissipation. Simply increasing fin quantity can hinder cooling performance by restricting airflow. Iteration 1 is recommended as the final design due to its lowest maximum chip temperatures of 53.50 degrees Celsius, ensuring a safe operational margin. It features a rectangular fillet fin design that enhances airflow and supports stable convection, leading to uniform temperature distribution across the fins. Thus, effective passive cooling hinges on the optimal fin geometry rather than material volume, validating the synergy of theoretical analysis and simulations for heat sink design optimization.